everyone. So our next speaker is David Rushenbach-Teller. He will present about performance. He's a guy from the performance team in Mozilla, and so we'll show you what he did recently and maybe how you can help more.
Thank you. Hi. So I have the complicated name that she just gave. You can call me Yorick, because that's kind of easier to remember. And yes, as Karen just mentioned, about performance monitoring. So what's about performance monitoring? Let's start with the simple troubleshooting session. People who are not happy about their Firefox. So let's start with the typical session. Hey, Firefox sucks. To which the only thing you can say is, yeah, sure, we're going to do that. Okay, let's try something a little bit more troubleshooting friendly. Sometimes Firefox sucks. My Firefox sucks. In that case, quite often we suspect that it's the add-ons, because the user has a behavior that we cannot reproduce on our machines, that nobody can reproduce. And given that there are so many add-ons in the wild, including quite malicious ones, that is a valid assumption. That's not always an add-on. Sometimes it's a bug, sometimes it's a driver issue, but often it's an add-on. Of course, we have the problem, which one? Many users have many add-ons. I have something like 12 installed. I've known people with 30 or 40. And then you find out when one of your add-ons is causing an issue. So we want to go to, well, ideally we would like to replace the Firefox sucks part by, maybe I need to uninstall this add-on. How do we do that? Well, we have basically 3 things we need to do. First thing, we need to find out what's running, which add-ons are running. We need to find out if they're slow or if they're slowing down Firefox. And then we need to find a nice way to tell the user. Well, this is the work of performance monitoring. So let's go through So what is currently running? I'm not running, but actually it could be running my Firefox. What is running on my Firefox? I don't know how familiar you are around here with execution models and the notion of stack, so I'm going to start with something simple. This is completely invented JavaScript stack. So, some part of Firefox is causing opening of a tab. And this tab opens with an innocent looking blog that decides to, perhaps less innocently, put a Facebook button. Always good for performance, the Facebook button, and for better. So Facebook decides that, hey, since there is a Facebook button, maybe we should try the user, and load lots of memory. So this calls that, this calls that, this calls that. And it turns out that we have adblock class installed. And adblock class is going to check whether it thinks that this is something that should be removed. So we're going to think a little bit inside, another way of thinking, and then maybe it's going to call back into the code of Firefox. Again, it's an invented stack, so I don't think that it actually works exactly like that, but it's an example. So it's going to call back into the C++ code of Firefox, because extensions quite often do that, to get some information, and who knows what happens there. And at some point, the C++ code is going to point to something that has been hooked into by another add-on, ghostery in that case, and ghostery says, hey, I know, something, whatever. Eventually, this is going to call back into adblock, who knows, who has no information necessary to decide whether it needs to leave this big chunk being displayed or loaded or not. Okay, so to the question, what is currently running on my Firefox? The answer is all of that. and a few others. But it's a start. So let's get rid of the part that's not really interesting for us. We don't care about what exactly which line of code, which part of the code is running from each extension or from each web page. We are just interested in knowing what we call compartments. Compartment is basically who owns this piece of code. So compartments are slightly way more complicated than just an URL, but for our use case, it's almost the same. So we can replace this. Compartments know to who they belong. So they know to which tab they belong. They know to which add-on they belong. So we could replace all of these. For instance, I should have done that by tab number 47. This is a compartment from tab number 47. These are several calls that belong to add-on plus compartments. Actually, in my example, the same compartment, but an add-on has several compartments. And this one is another compartment. So, by inspecting the memory representation of the JavaScript code that's being executed, we can find out who the code belongs to. So we have a way to answer the question, the first question, what is running? We have not decided exactly when we would inspect the stack, but inspecting the stack is to finding out what's running, and then to finding out how slow things are. So let's go to part 2. How slow are things? There are several possible approaches to that. Intuitively, we could decide that we just need to measure how long we are spending executing each thing. So this has JavaScript code. Let's start the clock when the code starts executing. Stop the code, stop the clock, at the end. Actually, stop the send watch. And then we do the same thing for this, the same thing for that. We don't need to have another send watch here because it's actually the same add-on. No, we also don't need here because this is executed by that. So we just need to measure once for each add-on at the same time. Another one for those three. And if we sum things in the end, we will, in theory, have information how much time was spent between now or in the last 10 seconds, for instance, running at .plus. So this has a very nice properties. It's very simple to implement. We just have to modify a little bit the JavaScript virtual machine to start and stop the clock at some point, and then to write the results. And we get data basically in real time. It has two problems. The first problem is that at this scale, measuring time is pretty slow. I don't have the actual numbers. I had them at some point. But it's slow enough that we had at least one benchmark that was slowed down by 20 or 30% just by measuring time. This was an extreme benchmark that was affected. It's basically the worst case scenario. It kept changing compartments all the time, going between. But it's a possible use case, and this possible use case demonstrates that this is not a technology that we can implement like this. And no, there is a second interesting thing. Clocks. At this scale, clocks are not reliable. An extreme example is the default clock, the default system clock used under Windows XP, which has a precision which is roughly 16 milliseconds. So we are dealing with code that can be executed sometimes for a few nanoseconds. and sometimes that's not advanced at all. So it's funny, I had a reproducible example in which I had an infinite loop. And I was taking the time, all the time, and the time didn't change, ever. 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 Under Windows only. But okay, there are better clocks in all systems. And these clocks tend to have another problem. Instead of stopping, or instead of jumping by increments of 16 milliseconds, sometimes they go back in time. Because they're so precise that they depend on the CPU on which you're running. And at some point, the OS might decide to move your browser or your process or your thread from one CPU to another CPU. And they do not have the exact same clock. And sometimes, so the time goes backwards. Which is actually something we're going to use later. Maybe not like this. But it is always an interesting experience to have your benchmarks that shows negative time with iterations. So that's actually not a complete blocker, because there are ways to deal with this level of uncertainty. I'll discuss that later. But that is a blocker. If your clock is so slow that it changes the measure, don't measure like this. So there is another technique that's used commonly. It's called profiling, with a sampling profiler. So this is pseudocode for something that could implement a profiler. Of course, it's simplified. So what does it do? Every 1 millisecond, for instance, my illusion of having there. So every 1 millisecond, we get the entire stack, the one I showed earlier, copy it, then look at all the threads and say, hey, this is on the stack, so yeah, it's present, so it's taken 1 millisecond. All of this is part of my milliseconds. And 1 millisecond later, we'll see again if it's not there anymore, so it was just 1 millisecond. And it's actually a technique used by all profilers these days. So actually that works. Whether the numbers in terms of milliseconds are reliable or not is an open question. But this technique is sufficient to give you a good idea of which of the things are taking time. It needs plenty of post-processing once you have all the data, but eventually you get there. You get the information. We actually have this thing implemented at least twice in Firefox at the moment. There is the profiler, which is part of the dev tools. There is the Gecko profiler, which is actually the same thing. So it's just one implementation. And there is a second implementation, which is the background hang reporter, which uses this with a very high latency, so it's not trying to be precise to 1 millisecond, more like 100 milliseconds. And if it sees that something is spending too many 100 milliseconds doing nothing, or apparently doing nothing, then it says, oh, it's a crash. And it starts all sorts of, at least error reporting, which let us debug Firefox. So, what's good with a profiler like this? The first good thing is actually the second in my list. People use this all the time. It's a tried technique. It works. The second good thing, we have the problem of things being too slow with the previous approach. This one, well, everything is running on a second thread. That thread is basically just collecting data. The main thread is not blocked ever. So you're not slowing down the main thread, almost. And if you find out that you're slowing down the main thread, you can throttle it. So that's a good thing. No, there are bad things. Well, one thing, it's pretty hard to implement this get stack if you have one thread producing the stack and the other one reading it. It's not the only thread safety issue, but it's one of them. The post-processing is typically quite long. If you have ever run a profiler, you will see that it takes a few seconds to display the results because it has so much data. And so that is much more annoying because you have suddenly two threads one of them keeps being awake all the time. It wakes up all the time to grab data from the other thread. And so your process is never sleeping. Possibly your CPU is never sleeping. So that's bad both for CPU use, which is battery. It prevents the system from swapping your process to disk. So it's bad for overall memory usage. And that's two bad things. So we tried a third technique. This one is called the RDTSC. RDTSC stands for Real Timestamp Clock. It's an instruction that has been present on all recent Intel processors and AMD processors. There is an equivalent for ARM, but we have not implemented it yet. You have a clock on the CPU. It tells you how many times the clock has turned since you started your CPU, so basically since you started your computer. The good thing is it's pretty fast. You just need to read a register from the CPU. There is nothing more to it. The difficulty is that it's very much not synchronized between CPUs, because CPUs try to go to sleep as often as they can. If they go to sleep, the clock does not increase. So if you have a process or a thread which is running on one CPU, and it has numbers from that CPU, and then it's moving to another CPU, and no, it has numbers from another CPU, but maybe the other CPU has run 10 minutes fewer than the previous one. So you have gone back in time by 10 minutes. And then you're going back and moving forward in time by 10 minutes. Which makes things interesting. It works, but it's a bit more complicated. So how do we do that? How do we make it work? We actually take the measure using a clock, OS clock, when we start executing code. And then we take the measure when we stop executing code. This is a very slow thing, but we only do it once. We don't do it for every compartment. We do it once per cycle. So theoretically about once per 16 milliseconds. 16 milliseconds, hey, great, that's basically the worst case granularity we have. So this has very few errors because we can use a relatively high precision clock. We can afford to use a slow clock because we use it seldom. And then, for every case here, we use the very fast one, the very fast and very reliable one. Once we have done all of this, once all this execution is complete, this very fast and very reliable one sometimes is going to give us good results. And we throw them away. We don't care about having results all the time. We just want to find out when something is slowing down the computer. So if we don't detect it the first second, we can detect it the second or the 10th second. If it's slow, it's going to be slow enough to annoy the user. It's going to be slow enough, often enough, that we eventually find it. And this very fast clock just gives us a proportion of the times of that time. So if this took 50% of the cycles that we got here, then most likely this took also 50% of the time. I'm talking about CPU time for people who know the difference. So all in all, statistically, we are going to end up very often with data that's accurate. By using the high precision clock on top, we have bounded the maximal error. We're not going to say AdBlock Plus just spent 10 minutes, 10 seconds or minutes working just because we have changed CPU in the middle. Worst case scenario, we're going to say, if it just took 16 milliseconds, hey, AdBlock Plus took all of the 16 milliseconds. And if it's just 16 milliseconds, we're not going to even report that because we don't care about if all the execution took 16 milliseconds because the user is never going to notice 16 milliseconds. No, if the entire execution took 2 seconds and AdBlock Plus seems to have been 50% of the time, then we're going to report something. So what do we gain? Basically, so it's extremely fast. It's not noticeable. it doesn't really cost any battery because we're not preventing anything from sleeping. So we have errors, but they're bounded. And the cons is we cannot trust each individual result. We just trust that if we average the result, then we're going to get something usable. I'm saying average, but I'm assuming. So this should answer the second question, how slow is it? Unfortunately, when we did that, this was not exactly the experience. Many bugs were open. Basically, that sounds like this is inaccurate and annoying. So annoying, I'm going to talk about that later, completely true. Inaccurate, this is, well, this looks true. Because although our measures are eventually accurate, we have missed one question. It's slow. Is the user going to notice? Because sometimes Firefox or anything is going to slow down and the user is not going to notice. And if you tell the user, hey, that add-on is slowing down your Firefox, and they never notice that the Firefox slowed down, they're going to think that something is broken. So, typical example. Did it slow down when the user was away? Sometimes I went to the bathroom, came back, and told me Firefox is slow. I don't care. I want to do something else. So, if I'm not in front of the screen, get rid of that information. It's not slow if I'm not in front of the screen. It's a false alert. But also, quite often, we have a slowdown when the user is in front of the screen reading. There is no animation, nothing is moving. There is slowdown. Who cares? The user cannot notice it because the user has just his eyes looking at text. So in this case, it's not a slowdown, at least not as seen from the user. And that's something that took us time to pinpoint. So basically, the two cases where there is a slowdown is the user is currently either looking at something animated or writing something or moving the mouse, is expecting something to happen. And remind you that you are trying to get out that multi-process Firefox, and the slowdown is in the process that the user is currently looking at. So these are questions that we needed to have to finally get the answer to how slow is it. Yes, we have results, we can report them. So I'm almost out of time, so I'm going to do it quickly. The first kind of report we have is through telemetry. So through telemetry, we have information on how many times each add-on has slowed down the computers of users. So the furthest to the right means bigger slowdown, the higher means more often. And it's indexed by the ID of the add-on. Some of them are readable, some of them are not. So this information is available to anyone, including us, add-on developers, users. We hope to use it. We hope that add-on developers will use it to find out if their add-ons are slow. We hope to use it to find out if we are causing slowdowns in the add-ons. And we're going to use it with the Go Faster initiative. A number of features of Firefox are actually add-ons. And so we can find out whether these features are slow like this. It's not the only mechanism, but it's a mechanism that we get for free now. Hopefully we would like to be able to recommend to users, are you sure you want to install this? It's pretty slow, you know. And your computer is not exactly fast either, so it might not be a good idea. And then we would like another form of self-support. So if you've been using Firefox nightly for the past 6 versions, so you've had a very nice yellow bar that's telling you very interesting things. And I'm sorry for that yellow bar. I'm not the one who landed it, but I should have removed it. So that was our first attempt to help users help themselves by uninstalling add-ons that are slowing down their Firefox. It was enough. There is a second attempt that's going to land, I have no idea when, which will look a bit more like that. On startup, sometimes Firefox is going to notice that something is wrong. It could be the slow add-on stuff. It could be that it has detected malware. I mean, it's going to be a great number of different features. But one of them is going to be, Firefox seems to be running slowly. I think I have an idea of how to fix it. See the statistics and what is causing it. Do you wish to try with me for a minute to fix this? And it's just one thing at startup. If we notice that the user is probably unhappy about their Firefox, it's probably slow. Of course, it would be great if we had some kind of task monitor, like this one in the OS. So we actually have one. And for free, it also tells you which of your tabs are causing Firefox to go slow. So in this case, it's pretty active about all the tabs except about except this one. Well, I'm going to close it. I just have opened it twice. Well, yeah. Okay. Thank you for listening. If you have questions,